American Meteorological Society's policy program is supported, in part, by a public-private partnership.
The economic impact of lightning essentially is damage to ground-based assets and operations and revenue loss associated with that.
Our first speaker is Dr. Amitabh. He's a scientist and technical product manager at Vaisala Inc., where he works to improve the performance of lightning detection networks around the world. He is also a member of several working groups on lightning locating and thunderstorm warning systems. Dr. Nag.
There you go. So I'll be talking about lightning and its economic impact and the various sources and types of data that are available today from modern lightning locating systems, and then look at examples of such data set. And the three of us actually have planned it such that, where I leave off, Scott picks up, and then when Scott picks up, leaves off, Kevin picks up. So it'll be a continuing theme of topics. Lightning, as we know, for folks who are new to this area, is an electrical discharge that is transient and is high current and transfers charge between different parts of the atmosphere or between the atmosphere and the Earth's surface. Primary sources of lightning are thunder clouds, also known as cumulonimbus clouds, and within clouds we have separated charge regions that produce lightning. And here is a nice picture that shows two broad kinds of lightning discharges, essentially those that occur within clouds and those that touch ground. The ones that are within clouds are, we can use a catch-all term called intra-cloud discharge. The acronym is IC. And those that touch ground are called CGs. About 3/4 of all lightning is within clouds, and about 1/4 touches ground. However, it is the part that touches ground that is of relative importance to folks on ground as well as ground-based assets, because that is the one that causes more damage. However, also the importance of cloud lightning is becoming apparent as we look into certain applications like warning and forecasting. So there are active research is going on in this area where we are looking at the cloud lightning discharges and what the efficacy is when we add cloud lightning discharges in the mix in various applications. Now, overall, when we talk about impact of lightning, the first thing that comes to mind is, of course, fatalities and injuries to human beings and animals. Over the past 10 years, on average, about 32 people have been killed per year, and 300 injuries have occurred each year from lightning over the US. And the number has been declining steadily, which is good, and it's a large part of the efforts of various people in the lightning safety area. Lightning used to be the second most effective weather-related killer in the US. It's now become the third most effective, thankfully, behind, I think the first one is floods and the second is tornadoes. And as a result of the threat of injuries and death from lightning, of course, it has applications in the area of outdoor events, recreational activities, whenever that happens. That needs to be managed, and venues, outdoor venues need to be managed, and Kevin will be talking in more detail about that part. And Scott will be mentioning specific examples of fatalities that happened this year from lightning to give us an idea of what we are talking about when it comes to human deaths. Now, the economic impact of lightning essentially is damage to ground-based assets and operations and revenue loss associated with that. And the specific areas that we can focus on is damage to anything, I mean, whether it's nuclear plants or homes or buildings. And there are forest fires that are started by lightning. There's impact on transmission distribution grid and wind farms and wind turbines specifically. Impact on air travel. We've all been delayed. Our flights have been canceled because of lightning in the vicinity. And spacecraft launches are also affected by lightning, where they have to do enormous amount of planning at, for example, the Kennedy Space Center when they are doing launches based on where lightning is. And there's impact on mining, on onshore and offshore drilling, and also on sea and airport activities. Downtime due to lightning causes loss of revenue, essentially. And now, all these wide-ranging economic impacts are, we don't have numbers that are well compiled that will give us sort of an idea of a dollar amount that, okay, so due to lightning, this is what the loss is. However, different industries have done separate studies that give us an idea of what the impact is in these areas. For example, a recent study by the Insurance Information Institute states that over 100,000 homeowner insurance claims associated with lightning damage incidents happened in 2013, resulting in a payout of $750 million, close to that number. Now, this number was slightly higher in the prior 3 years of 2010 to 2012, the average being about $1 billion a year of insurance payouts due to lightning-associated damage. And about 23,000 building fires occur each year on average due to lightning, resulting in about $500 million in property damage, according to the National Fire Protection Agency. And about 9,000 wildfires are initiated by lightning, and that's the average over 2008 to 2012. And while fighting these fires, on average, 4 firefighters are killed per year due to lightning-initiated fires. Now, these aren't counted in the overall fatality numbers that I mentioned in the previous slide, because these are thought to be fire-associated deaths rather than lightning-associated deaths, but these really can be accounted for if we think of it that the lightning started the fire which killed people. And these numbers come from the National Interagency Fire Center and NFPA. And we are already getting a sense that there are billions of dollars of primary and secondary effects that we don't account for from lightning, when it's, whether it's outages in transmission distribution lines, whether it's damages to wind turbines, or whether it's stoppage of activity in ports because there's lightning in the vicinity and there's a safety factor associated with that. Now, because of these wide-ranging impacts, we can say that there are a wide variety of applications of lightning data, and we can divide that those applications in these generally broad areas. For example, the meteorological area includes applications in lightning warning, nowcasting, and forecasting. The National Weather Service uses lightning data, has been using it for decades, along with other weather information like radars and satellite to support its mission of protecting life and property. Lightning data can be ingested into global and regional models to improve forecasting for severe weather. So it can provide us with improved forecasts. There is a relationship between increased lightning rate, known as lightning jump, and following severe weather. And currently there is research ongoing to examine how to assimilate that information in forecasts in a way such that we get reliable estimates with low false alarms. And then, of course, there are other applications. We talked about the airports applications. The Federal Aviation Agency uses lightning data. The Air Force Weather Agency uses lightning data. And there are applications in the area of insurance, as we saw in the last slide, mining. Our defense forces need lightning data, not just over the US, but wherever they're operational globally. And now let's look at an example of use of lightning data in the energy space. So based on a survey by of US power utilities performed by EPRI, the Electric Power Research Institute, in 1996, lightning was found to be the single largest cause of outages on distribution and transmission lines in lightning-prone areas. Utilities in the path of intense storms can actually plan their activities around those storms and can prepare for the storms by alerting repair crews and dispatching them to areas where there are expected to be outages due to lightning. And use of real-time lightning data has been shown to actually reduce maintenance cost and improve reliability of our transmission and distribution lines. And additionally, archived lightning data along with data on faults online together can be used to improve the reliability of lines by prioritizing line upgrades, essentially improving the quality of the grid. Now, these applications that are talked about right here are the ones that actually drove the development of technology in the 1980s and 90s that led to the deployment of a nationwide network. Now, this was actually done in partnership by the government, academia, and industry. It was funded by EPRI, the Electric Power Research Institute, and NSF, and later was expanded in partnership with the Bureau of Land Management, NASA, and SUNY Albany. And later it was commercially owned and operated by Global Atmospherics and now Vaisala, and today it is known as the US National Lightning Detection Network. It has been operating continuously since 1989, providing continental scale lightning data. And it has, as technology has improved, undergone several technology upgrades in various years, the latest one being in 2013. The modern day NLDN provides total lightning data, as we call it, both cloud and cloud to ground data. And along with partnership with Environment Canada, actually covers a large part of Canada and the United States. Now, the NLDN is just one example of several lightning locating systems using different technologies that operate in the United States, covering either the whole country or different parts of the country. And these networks are operated by either different commercial entities or by government and academic institutions. So the progress of technology has really led to more data being available, which is good because data sets often complement each other, and I'll be talking about that in the coming slide. Now, when we talk about lightning detection, what are we really talking about detecting and geolocating? Well, we are talking about electromagnetic signals that are radiated by lightning. Now, lightning discharges may last for a second or more, and individual processes in these discharges have a wide range of durations. They can last for several hundreds of milliseconds to less than a microsecond or tens of microseconds and less. Now, that means that in the frequency domain, they can have frequencies ranging from a few hertz to 10 to the power 20 hertz. And the electromagnetic signals from lightning propagate, as shown in the diagram over here. Shown also is the lightning power spectrum, which peaks in the very low frequency range. The peak is around 10 kilohertz. And at this frequency range, as you can see, since the power is the highest, the signals propagate the farthest distances, either as ground waves or as waves reflected between the Earth and the ionosphere. So the Earth and the ionosphere act as a waveguide to transmit the waves from their source to sensors that may be as far as thousands of kilometers from the source. So this would be techniques that would be used in either geolocating lightning globally using long-range lightning locating systems, or in systems like the US NLDN that are on a continental scale. Now, the VHF radiation from lightning, or the very high frequency radiation from lightning, the radiated power is relatively small, and as a result, these signals get attenuated very fast and can only travel as line-of-sight waves directly over the Earth's surface over 10 to about 100 kilometers. And finally, optical signals from lightning are radiated as a result of heating effects of lightning on channels, leading to optical emissions that can be detected by various imaging equipment, video cameras or regular cameras, either on spaceborne platforms, space-based platforms, or on the ground. Now, the fact that there are from the same lightning flash, there can be different types of emissions at different frequency ranges, mean that we can take different types of detectors, tune them to these frequency ranges, and get information that is complementary in nature about the same lightning flash. These detectors can either be ground-based, for ground-based networks, or space-based and satellite-based. For ground-based systems, they typically consist of a minimum of 4 to 5 sensors on the central processor. Now, if you were to increase the size of the network, you would need, as you increase the coverage area, you would need more and more sensors or detectors. This is the minimum that you generally require. And each sensor measures the electromagnetic signal produced by lightning processes and send that information back to the central processor. The central processor is essentially algorithms that take information from multiple sensors about the same lightning event and then geolocate it, meaning that they essentially calculate a latitude and a longitude and some other characteristics of lightning that are put on a map. Satellite-based lightning locating systems, most modern satellite-based lightning locating systems essentially are CCD array-based optical detectors, charge-coupled diode-based optical detectors or imagers, on low Earth orbiting satellite platforms. That's what currently is available. There are also VHF direction finding techniques that are used to geolocate lightning from space. Now, the examples of satellite-based detectors are the lightning imaging sensor on NOAA's TRIM mission, the Tropical Rainfall Measurement Mission, and there's also the DOE satellite Forte with its own lightning imaging sensor, lightning locating systems, space-based lightning locating system. And the first geostationary satellite-based lightning locating system is expected to be launched in April of 2016, called the Geostationary Lightning Mapper on the GOES-R platform. Now, in the next slide, which looks a little bit heavy, what I've done is I have compiled various types of lightning locating systems based on whether they are ground-based or satellite-based, and different frequency ranges in which they operate, and the different areas which they cover. Now, this information comes from various studies, validation studies of performance characteristics of different types of lightning locating systems. Now, if you were to take all this information and try to make some broad and general statements about the performance of different types of lightning locating systems, this is what it would look like. So, ground-based, very low frequency, long range lightning locating systems provide global coverage with a spatial resolution of 2 to 10 kilometers. Primarily, they detect cloud-to-ground lightning and tell us when and where lightning touched ground. Ground-based, low-frequency lightning locating systems, you can think of them as the NLDN type of networks that provide continental or country-wide coverage, have a spatial resolution of a few hundred meters, so better than long-range systems. They detect and geolocate nearly all cloud-to-ground lightning and a large fraction of cloud lightning, and tell us where lightning struck ground. Now, I keep repeating where lightning struck ground because it is important, as we saw in various applications, to know where lightning struck ground. But it's also important in various applications to know how much cloud lightning there was, because there are applications in the area of warning and forecasting. So if we were to pull at that thread and go to the very high frequency range, then you are able to improve the spatial resolution of the data. So you can provide coverage over a smaller region on a regional scale, but then have spatial resolution of 100 meters or better. And VHF lightning locating systems detect and geolocate nearly all cloud-to-ground and cloud lightning. So they detect almost all lightning. However, because of the nature of the emissions detected by them, they are generally not able to accurately tell where lightning struck ground. Now, VHF lightning mapping systems are actually pretty unique in the sense that they provide us with information that allows us to draw pictures of lightning channels by joining the dots that are latitude and longitude representing individual sources. We can essentially draw pictures of lightning channels. I think, Scott, you're showing an example of that. Satellite-based lightning locating systems are somewhat similar to VHF systems. However, they operate on a larger scale, continental and countrywide scale. They provide that coverage. However, it depends on the field of view of the instrument on board the satellite or the number of satellites used. And they provide, however, a spatial resolution of 10 kilometers. The data has a resolution of about 10 kilometers. Depending upon where nadir is and where the field of the edge of the field of view is, it varies a little bit. They detect and geolocate nearly all cloud-to-ground and cloud lightning. So this is also lightning mapping data, but they cannot tell us where lightning struck ground. Now, low Earth orbiting satellites, because they are low Earth orbiting, would monitor each point within the field of view on the Earth's surface for about 90 seconds to a few minutes. If it's a geostationary satellite, then you'd be monitoring the field of view continuously, and that's what's coming in with the GOES-R and the GLM. Now, since different types of lightning locating systems are sensitive to different aspects of lightning, they provide unique information and complementary information to each other. And in addition, they provide some matching information. And actually, Scott will be presenting a study where he has taken ground-based and satellite-based data and examines what that match is and what that matching information is. And here is an example of a data set, a high-resolution cloud-to-ground stroke data set. The different taken from 8 years of ground-based lightning data. And this color scale shows the number of strokes per square kilometer per year in different parts of the country. The purple color indicates, purple and blue indicates the areas where you have the largest amount of lightning, and of course the lightning capital for the United States is Florida. And there is very sparse amount of lightning along the west coast. And this data set, these types of data sets, the long-term lightning data sets, can and have been used for climate studies, including examination of the relationship between temperature, convective available potential energy, and change in lightning as a factor of as a function of those two parameters. Now, the other application of such long-term lightning data sets is essentially being able to compile statistics and be able to look at a map like this and be able to tell what type of lightning protection parameters you would need on things that you're building on ground. So based on what your exposure risk is to lightning, whether it's a wind farm or whether it's a building that you're building, there are codes that tell you what level of lightning protection you would need. So that's another application of something, data set like this. And finally, you can extend that data set when you're looking at it from a global perspective. Long-range global lightning locating systems would provide you with lightning stroke density maps that look like this. This is a 3-year map, which essentially shows the 3 chimneys of the world, where you have the most amount of lightning in the Central and Southern Americas, Central Africa, and the Asia-Pacific region. And such data sets, again, can be ingested into models that will allow us to improve forecasts and improve, essentially, climate studies. And additionally, this is relatively important for data-sparse regions, where there aren't many meteorological data sets available in different parts of the world. Lightning data can be used as a proxy for weather information such as radar reflectivity or rainfall, convective precipitation estimates. So lightning data is, that is collected using such systems is quasi-real time and allows us to monitor the globe continuously and produce data in regions where we don't have access to data readily. So finally, to summarize, lightning has significant public safety and economic impacts. Typical users of lightning information include national, regional meteorological agencies, aviation or air traffic authorities, including space launch facilities, land management entities, forest services, electric power transmission and distribution operators, wind farm operators, and other public utilities. Ground-based and satellite-based lightning data are sensitive to different aspects of lightning and hence provide us with complementary information. And understanding the characteristics of these different data sets allows us to use such data properly to improve the efficacy of different applications. Thank you.